Today we will be talking about nomenclature and shape. I will be showing a tutorial for ammonia NH3 as an example compound. We will go over how to name it by using nomenclature rules and how to explain its molecular shape and real-world applications. First thing we have to do is identify the compound type. What type of elements are present in NH3? Both nitrogen and hydrogen are classified as nonmetals on the periodic table. This means NH3 is a molecular covalent compound. They are both nonmetals because they share electrons to form a stable molecule. The second thing we will do is apply nomenclature rules for covalent molecular compounds. In NH3 we have two elements. The first element's full name is used as it appeared on the periodic table. So in this case it would be nitrogen. The second element is named as if we're an anion. So we would take the root element name and add the ending "-ide". In this case we have H, which is hydrogen, so that would turn into hydride. Covalent compounds use prefixes to indicate the number of each type of atom. The first element, nitrogen, does not get a prefix if there's only one atom. The second element, hydrogen, gets the prefix tri for the three atoms in NH3, so we get trihydride. We put the prefix only in front of the second element, so together we get the systematic name nitrogen trihydride. But the common universal name is ammonia. Ammonia is the name that is widely recognized and used in everyday language and is used universally in labs and industrial contexts. Sometimes for simple molecules, the common name is preferred or required. Some of ammonia's real-world applications include fertilizer manufacture, since a source of nitrogen for crops. Ammonia is also in household products. It's a well-known ingredient for cleaning supplies. Ammonia is also used in industrial refrigeration for air conditioning systems because it absorbs heat. Now we will go over the shape and hybridization of ammonia. First we will do electron arrangement. We start with the central atom, which is N, with 5 valence electrons. Nitrogen has 5 valence electrons because of its outermost shell, so it's placed in group 15 on the periodic table. While hydrogen only has 1 valence electron, but since this is NH3, we will combine them so we have 5 plus 1 times 3, which equals 8 valence electrons. When we draw the electron arrangement, we can see that it forms 3 bonds, which comes from the 3 hydrogen and has 1 lone pair. In total, we have 4 regions or domains of electron density around nitrogen and ammonia. 3 bonding pairs from the NH bond and 1 lone pair. Each NH bond is a sigma bond, which are formed from the overlap of H1's orbital and nitrogen's sp3 orbital. Each hydrogen forms 1 sigma bond with a central nitrogen atom. Ammonia has no pi bonds because all the bonds between nitrogen and hydrogen are single bonds. This helps us understand both its molecular geometry and its hybridization. Now we move on to electron geometry and molecular geometry. Ammonia's shape is a tetrahedral because there are 4 regions in total. 4 electron groups take a tetrahedral arrangement to minimize repulsion. For molecular geometry, it's a trigonal pyramid because the central nitrogen atom has 3 bonded hydrogen atoms and 1 lone pair of electrons, which causes the shape. Ammonia has a bond angle of 107 because the lone pair of electrons on the nitrogen atoms repel the 3 bonding pairs more strongly than the bonding pairs repel each other. Ammonia has a polar covalent bond because the bonds are formed by sharing electrons between 2 nonmetals, nitrogen and hydrogen, and the difference in their electronegativity creates an unequal sharing that makes the bonds polar, or in this case, moderately polar covalent. For hybridization, we focus on nitrogen because hydrogen cannot hybridize because it only has 1 single atom, which is 1s orbital. We need 2 or more orbitals to make hybrid orbitals. For the hybridization of nitrogen, we obtain sp3. We get this from the 1,2s and the 3 2p orbitals, which forms sp3 orbitals, which are used for the NH bonds and the 1 for the lone pair. So when we combine the 2s and the 2p, we will get sp3. But since ammonia is a tetrahedral, and so it would have 4 domains, so usually when there's 4 domains, it would always be an sp3 hybridization.